First click OK, and then double click. Okay. Give it homework. 9, that is due. 16 Tuesday. We introduced the idea of Poisson bracket, and let's try to gain some more insight into it. And keep in mind, earlier we have talked about symmetries and transformations. So we want to connect somehow these quantities. Remember earlier, we said whenever there is a symmetry in the Hamiltonian, then there are some conserved quantities that come out. In general, how do transformations work in this context? That's what we're talking about. So broadly, we're talking about Poisson bracket. This becomes very relevant because this is the connection between quantum mechanics and classical mechanics, the closest connection we can have. And we'll almost write down Poisson brackets here as we proceed, and you will see a lot of similarity between the quantum mechanical equations that we are, permutation relations that we write. So remember, we have introduced, we're talking in terms of Hamiltonian. So Hamiltonian is a position dependent quantity, it has a momentum, and it has a time dependence. And whatever the time dependence is there in the position, we say it is implicit. So that's our understanding. T is time dependence is implicit, and T is the explicit time dependence that is there in the Hamiltonian. The action is a functional of both position and momentum. We have T1, T2, T. This is also defined out. Often we write this as velocity V minus of h. That's your action. And we showed that our action, the variation, the total variation in the action. And if you use the stationary action principle also, this gets contribution only at the boundary. D by dt of, let's say, G of T. That's here. And this is called a generator, T, generator. And when we say generator, it is a generator of what? It is a generator of dynamics. Like this is how particles move, because everything else has been made zero. So whatever is remaining is how the particle evolves in time. So this is the generator of dynamics. And this is equal to P with variation delta R minus H T. And we have other quantities, for example, dr by dt is equal to partial derivative of the Hamiltonian with momentum d by dt is negative partial derivative of the Hamiltonian with position, and the total derivative of the Hamiltonian itself is just the partial derivative. That's Hamiltonian. This means that even though R and T has time dependence in it, they sort of cancel each other out. The time implicit time dependence in R, implicit time dependence in T, they cancel each other out. So if you want conservation of energy, then you want no explicit time dependence in the Hamiltonian. If you want conservation of linear momentum, then you don't want any position dependence, or at least explicit position dependence in the Hamiltonian. The Poisson bracket we introduced is, suppose you have F and G. This is the Poisson bracket. And it is with respect to some positions, R and P is defined as partial derivative of F with respect to position, partial derivative of G with respect to P. And these are vectors now. Take the dot product there and swap the derivatives and subtract. And in this form of writing, there is no hint of any quantum mechanics at all. But remember, like, and or the way you introduce it is that, suppose we were doing last time, what we did, sorry, was the total derivative of any function which is depending on R, P, and T is equal to the partial derivative of the function with respect to time plus the Poisson bracket between the function and the Hamiltonian. So there is one nice thing that comes up out of this, which is almost immediate, is if you were to do position, just the derivative of position itself, this is equal to, or not, let me not do that, maybe that we already used. So let's highlight, just for highlighting, let me say F is R and G is P. And this Poisson bracket notation. Okay. And then we immediately see that R, comma P. This is Poisson bracket. R, comma P. This is E R by R dotted with dp by dp. One has to be careful in this. So there is an I here, J here, and let's say this is K that is dotted. That's I, that's J. Many indices running around. And that's minus of the I with respect to dp. Okay, this time dotted with dp J. This is ER. Okay. And you immediately see that this is 0, that's 0. That is equal to a identity. This is equal to identity. So that's basically 1. And just for reminding, just to observe that if you were to do R, comma, P in quantum mechanics, here, and let's say 1 over IH bar, what is that equal to in quantum mechanics? Position and momentum, uncertainty relation. No. What is X comma P? Let's say X comma PX in quantum mechanics, the commutational version. IH bar, right?
Yes.
Good.
Yeah.
And what is X comma PY? X comma Px is IH bar, X comma PY, 0, right? Very good. X comma PZ, 0. And Y comma PY is IH bar, and so on. Like only the diagonal is 1, rest everything is 0, right? Okay, so overall, these are nothing but X, Y, Z, Px, Py, Pz. What can you say is this equal to? Right, it's equal to 1 because there is a diagonal and there is 0. So you would just say this is 1. That's the conical delta in there. So it's pretty much the same. If I divide, or you can either say there is an IH bar that is connecting the quantum commutator is pretty much the classical Poisson bracket with your IH bar showing up. So, so with that connection in mind, can I erase this? Also have the point that I think I was trying to do that there, but now that we have this connection between the Poisson bracket and quantum mechanics, dr by dt would be equal to Poisson bracket because the partial derivative with t is 0. So r comma Hamiltonian Poisson bracket and r comma p, and that's equal to, if you do this again, r with respect to r will give you 1, Hamiltonian with respect to p remains. So this is equal to the partial derivative of the Hamiltonian with respect to p. This equation of 4 should we already know. This is new. Right, in between that is there, that's new. This is in classical mechanics. And in quantum mechanics, this gets upgraded to same, everything remains the same, except now you say this is r comma h with h bar, and that's equal to again partial derivative of Hamiltonian. Notice these equations still remain in quantum mechanics. It's not that this disappears. The only difference is that the Poisson bracket becomes a commutation relation. This is still true. Nothing changes, only thing this might have operator representations to it. The interpretations change, but equations of motions will remain exactly the same. Again, classical mechanics, you have dp by dt is equal to momentum, Poisson bracket of the momentum and the Hamiltonian, and this is equal to minus h by oh. I've not evaluated these things, but I think in the last lecture we really showed this. And in quantum mechanics, this is still valid, except that now you have commutator taking the place of the Poisson bracket with the inclusion of IH bar. So already you see the connection. Again, I should highlight that Hamilton equations of motion are still valid in quantum mechanics. There is no change at all. Absolutely, the outer equality is still valid in quantum mechanics. The only thing that has changed is that the Poisson bracket has become a commutation relation. Let's go back to this generator and gain some insight about this Poisson bracket, because commutation relation seems to have exactly the same property as the Poisson bracket. So it is good to have some insight of what is Poisson bracket trying to do when it is really evaluating the between two operators. Same thing with commutation relations. We often say commutation relations of one operator with another operator. It is good to have a physical interpretation of what that means. There are multiple interpretations, but one of them is what I'm going to present here. Let's go back and look at the generator. So recall, move the camera. The pen is writing a little lighter, right? Today? Double. You guys are young and powerful. Nice.
I got glasses on too.
Hawk eyes. That's what it is. Eyes of a hawk. By the way, since you guys spend time in the students' launch, right next to the launch, there is this tree. A hawk has been visited. There's a nest made by a hawk there.
Oh, yeah.
And, oh, and recently there are chicks in there.
Oh.
Yeah, so you can see them actually. Yeah, so yeah, you check it out. Okay. Okay, so generator again. And April has a binocular, so you can really get a close shot.
Yeah, upload some photos to Facebook and so.
Oh, on
Some
Facebook, okay.
videos.
So it's also I'm linked. Very late. Cannot beat Facebook. Yeah, good point, yeah. But they will start fledgling wings very quickly and it'll be nice.
That's what I saw several like places, like small birds. So that's the hawks. Hawks chicks.
I haven't seen the pictures that.
Oh, yeah, I
April
saw, I
posted.
saw like I saw only one that day when I was sitting here.
No, that was the mother problem.
Yeah.
Like mother or father.
I saw something like that.
Yeah, like that, it is a red-tailed hawk. Because it has a very clear red tail when it comes. And most of those who visit my office, they get to see it because they are facing the window. I never get to see it because I'm always facing the back. But I have seen it now and then.
Oh, I understand what until now I thought maybe that's feathers of the mother.
Oh, I didn't see. No, so like if you carefully see, there is a white head that comes out.
Yeah.
But now it will start growing, and when it is growing, it will start to fledge its wings, and that will be kind of nice. Yeah. So whenever you go to there, you will have some. Okay, so the generator is G is equal to P dotted with delta R and the Hamiltonian with time, right? So, and we are claiming that this is what generates the motion. And we also saw that there are some classic transformations that are useful. So we said delta R if it is equal to delta epsilon, which is a constant. So when I write this, this means it is constant everywhere. At every point in space, I move it by the same amount. That's what I mean there. And here the idea is that R prime is equal to R minus delta R. It can be plus or minus depending on whether it is active or passive representation I'm using. So this is a negative I'm pointing out here. And P prime is equal to T minus delta T. And the delta R for translation is this, so delta T in that case would be 0, right? So the first term is for translation. So you move your position a little bit and you don't do anything with
That's the
time.
initial time.
That's sure. Tell that again?
The initial time?
No, I meant this is the change in time when I'm moving something. So I'm saying that you're all sitting here. And while all of you guys blink your eyes for a moment, I move everything in this room by 1 centimeter. Or let's say 1 kilometer even, everything is, the walls, the tables, the room, you guys, the sun, everything is moved. And can you make any sense out of it, or is it even possible to observe? So that's a way you can ask the question, but that movement is encoded in this. I move like I'm pretty much moving the coordinate, I'm not just moving the particle, I'm moving the whole space by 1 meter. So that's what this means, right? The translation.
Kind of like Earth orbiting around the sun. It's 1 centimeter.
Yes,
Yeah.
and now I'm saying everything, including the sun. Sun has to be moved, Earth has to be moved, the whole universe, everything has to be moved, and that's the strict translation in a sense. So, and time, you don't change anything, that's translation. Rotation, what is it? We said, this is equal to plus, so now there is a rotation, this is translation, rotation. Rotation is angle, so how much you move, and this also has the information about the axis. You move an angle about an axis, which is the direction of this 3 vectors, and cross with R. Where R is the position of, R is this original R here. So it's a position dependent quantity. And if, for example, if your axis is here, if you're closer to the axis, you move little. If you're far away from the axis, you move farther, right? That's the dependence on the R. If you're farther, you move more from. And time doesn't change under rotation, right? So there is no change in time. Let's also think of Galilean transformation. If something is moving together, there is one object here and another object is moving, how will it go by? So you remember your x prime is equal to x minus vt, right? And t prime is equal to t. That's Galilean transformation. But I want to make an infinitesimal Galilean transformation, so I will say this is small, dv. There is an x, y, z, so r will be equal to r prime will be r minus delta v times t. Right, a small change in the velocity instead of the standard Galilean transformation. So the Galilean transformation, I'll put this here as delta v times t. Right, it has to be a vector, so that's a vector. And what is the what is the transformation in time? So that's plus delta t. So Galilean transformation is the only transformation that leads to a time variation. If you were doing relativistic physics, this is non-relativistic physics. If you were doing relativistic physics, these equations change a bit, and this gets more position dependence also. Time dependence depends on position in relativity. Like if you're going faster, or even just where you are depends on decides how fast your time is going. So that's what we want to do. Again, this is translation. And this is rotation. Oh, actually, this is not, this time is my bad. So r prime is equal to r minus delta v times t, and t prime is equal to t minus 0, right? Time doesn't change. There is no change in time in Galilean relativity, right? You don't change the time at all. So this is 0 actually here. So that's rotation, and this is boost if you want. And there is a new piece I put in, so this is 0 here. And in this, I put a time itself, which I should call it maybe epsilon 0. You can say epsilon 0. That's basically translation in time. So this is space, translation in space. And this is translation in time. And this whole translates to 10 operators here. Like there is 3 translations, 3 rotations, 3 boosts, and 1 time. So overall, there are 10 parameters in here. That's called the point correct algebra. But let's not worry about that. Let's actually make such a transformation, and let's look at rotations. Or before that, I should do something, right? Oh, what is my generator I have wrote, right? So let me write my generator. The generator for this complete total transformation that is possible would be equal to delta epsilon dotted with P. This dotted with P, this dotted with P, plus delta cross R dotted with P plus delta, so P times delta V dotted with P. Put the time there on the other side and plus, and now this is over, and then minus of H delta T, right? Since delta T is only got by translation, I want to not write that, it's just delta T, and delta T is understood to be a constant. So that's, but there is one small thing I can do, I can replace this cross and dot, then this is angular momentum, right? So this is equal to translation times linear momentum plus rotation dotted with angular momentum. Here I will say variation in the velocity. I'll dot it with a boost operator n minus h delta t. Here n is equal to p times t. P times t is called n. This is your linear momentum, angular momentum, n, and h. And in this form of looking at it, like remember in quantum mechanics, we often look at this as operators. I'm not saying these are operators at all, but you will notice that they have all the properties of an operator, except that we will be doing Poisson bracket. Okay, so that's your operator and or the construction of the generator if you want. Let's now try to see how things change under rotation. So let's start with, I'm going to stick to rotations at this point, just for simplicity. There is no reason to say it is rotation. I can say this is the whole Poincare transformation, and or whatever I'm going to talk about will go through, but it will be just more tedious. So we are going to keep it to rotation, and it's kind of rich in rotation. So let's start with time t1, t0, let's say, and position is r0. So some variable, and I make a transformation, make a rotation basically, and let me call that rotation delta 1. Like in this case, I write delta 1 so that it can accommodate for epsilon, beta, v, so on, but we are doing rotation, so it's okay to write delta 1. This is equivalent to saying, I think I talked about it before, if you have a remote, if I were to rotate this, first rotate it here, and then rotate it about another axis. Now the remote is facing me. I go back. So what I did was I rotated it about an axis that is Z axis and then about the X axis. But now I do rotate it this way and then rotate it the other one. So the order changes the position significantly. We are now going to capture the same thing, but infinitely tiny. We want to make two transformations and see how much off they are. And what's the connection between the 2 points, right? So that's what we're going to say. So that's the first transformation. First transformation took a certain time and position to T1 times R1. Under rotation, that's what changed, but time doesn't really change. So this is not really, time is just taking a ride here, so it doesn't do anything. And then I do the second operation, second rotation, so second delta 2 theta, and this, let's say, goes to T21 and R21. The first rotation, second rotation, and you get that, but I didn't have to do it in that order at all. I can do the second rotation first, and let's say I get T2 R2. And afterwards do the first rotation, and this time I will be entirely in a different place, which I will call it R12. And then finally, we want to do what's the connection between these two. And this one, we will say is, as you're seeing, this will lead to the idea of commutation relation. So I will call it 1, 2. And of course, there is no commutation relation here, that has to be read as a Poisson. So we'll see what that is. So we would like to find out what this is. So let's put this all together. So we will do this 2 times. First, we will do this just using simple transformation. Whatever matrices we will see is working here. And then we will come back and do the same thing with Poisson bracket and see what's the connection. So rotation involves this, right? Delta theta cross R. So we have R1 is equal to R0 minus of delta 1 theta crossed with R0. That's a definition, if you want, right? So that is only one piece here. That's the only transformation that is happening. I've not done translation, boost, everything is killed. So that's what's the transformation. R1 is related to R1. That's. Do the next one. So what is R21 now? R21 is equal to R1 minus of second one. So that's R1. Right. You start from R1 and reach R21, right? That's the definition. But now R1 is related to R0, so put this in. So R0 minus delta 1 theta crossed minus of delta 2 theta crossed with the thing. So it's a chain, like it's a recurrence in a sense. One affects the other. So first R1 is related to delta 1 and R21 is related to delta 2, and together it's all good. Expand this out. This is R0 minus delta 1 theta crossed with R0 minus of delta 2 theta crossed with R0 and plus. Now there's a double cross product coming in, delta 2 theta crossed with 1 theta crossed with R0. That's a total a total change from R0 to R21 due to these two transformations. Do the opposite. Now I reached R2, R1, 2. It's the same idea. So R2 is equal to R0 minus delta 2 theta cross with R0. And R1, 2 is equal to R2 minus delta 1 theta. And I'll skip this step, but it is clear what is happening. R0 minus delta 2 theta cross with R0 minus delta 1 theta cross with R0. So, and finally, we have plus delta 1 theta cross with delta 2 theta cross with R0. Pretty much got by swapping 1 and 2 from the first equation. And now I have a way of deciphering what this is, right? If I want this transformation, I just need to subtract these two quantities. So R2, 1 minus R1, 2 is equal to, so I subtract these two quantities. I want to decipher what this is equal to. First three terms completely cancel out. And I have delta 2 theta crossed with delta 1 theta crossed with R0 and minus of delta 1 theta crossed with I want to recognize what this is. So you have write this in the form of 1 is equal to R1, 2. And I want to write it as negative sign because that's what I want to read out my variation, right? So let me write this as minus of delta 1 theta crossed with delta 2 theta crossed with R0. Right, that's this term here. And since I'm going to write this, I've taken out a negative sign, so this is equal to negative, but I'll use that negative to flip R0. So this is equal to plus delta 2 theta crossed with flip this R0 crossed with delta 1. Remember A cross B cross C plus B cross C cross A plus C cross A cross B is equal to? Yeah, very good. That's zero. It's called Jacobi's identity. Very good, right? If you notice, this is A, 1, 2, let's call it 3 for a moment. No, 1, 2, yeah, 0, we'll call it 3 for a moment. 1, 2, 3, 2, 3, 1, which means that if I put it on the other side, this will be equal to 3, 1, 2. So this will be equal to R1, 2 minus of 3, 2, 1. So that's not crossed with and 3 and it should be a negative sign, right? So there is a plus. Okay, 3, 2, 1 delta 2 theta crossed with delta 1. I'll use one of the this guy. Use did I do this? 3, no, 3, 1, 2, right? 1, 2, 3. 2, 3, after 3 is 1, right? So 3, 1, 2, 3, right? So I'm going to introduce a negative sign by swapping this, 1, 2, minus of delta 1 theta, delta 2 theta, cross with R naught. But I can always put in, remember, R1, 2 is related to this higher orders, right? So this is R2, R12 itself. And when I replaced R12 is equal to R0 plus higher orders. When there is one more delta theta that comes in, then it becomes 3 delta theta. So it is higher order. So I can always replace R0 with R12. I don't lose anything. In this way of saying, this is what I mean by, so I recognize, so this is delta 1 Q theta is equal to delta 1 theta crossed with delta 2 theta. Right, that's the right. But that's standard rotations, infinitely tiny rotation, that's all. I mean, in general, if we were to do finite rotations, this is very messy. Like this will be matrices and it's very hard to capture the details in. We can see a nice pattern just because this is infinitely tiny rotations. So the same remote we're talking about, we do a tiny rotation and then we do a tiny rotation there and you change the order. So that's what we have. So keep this in mind. But now we want to see how can we learn this, or how does Poisson bracket capture this somehow? Okay. So any questions at this stage? This should be straightforward in the sense that it's very geometric. This idea of rotation, the infinitesimal rotation. Now let's do Poisson bracket. And that should give us some idea of what Poisson bracket means, or for that matter, what a commutator means. In quantum mechanics, what commutator means. So here, you have a generator, right? So let's say generator of rotation is delta theta L, right? So rotations. Generator for rotation is delta theta with L. So if I want to make two rotations, I will make delta 1 theta. So let's say G1 is delta 1 and G2 is delta 2 theta dotted with L. And let's talk about what is here we are going to talk about Poisson brackets, but there is nothing wrong in thinking in terms of quantum mechanics. Commutator has the same property. So let's do G1, comma G2, Poisson bracket of R, comma P. That's equal to delta 1 theta times the angular momentum, delta 2 theta, angular momentum, and some bracket R, comma P. That's a new thing here. Okay. And if this was a commutator, what is this equal to? Oh, come on. Where is it? Oh. Okay. Thank you very much. Okay. If it was a commutator, what is this equal to? Any hints? Maybe I should specifically ask, what is the commutator of L and L? Huh?
0,
0?
1.
1? It's neither of them. It's not 0. Why is this not 0? Operator and operator, why is it not 0?
you're taking.
Being L,
Matrix and you-
L minus L, it's not zero. I'm saying it's not zero. No, you're not familiar?
If you take two, how many forms a square matrix, which. It won't equal zero, it depends on. Where the side here.
Huh?
They are leaving out of.
Because their outer product is good, that's a good observation, but what is that equal to? Very good. What is that equal to? That's very, you must have seen this. Maybe I'll change the notation a bit, maybe index. Out, I, J, no,
Does help, does help.
I had L,
I H hat, yeah, I H hat, yes, then.
the other component of it.
Other component, very good, so you say epsilon I J K L K.
Okay.
If this is 1, 2, this is 3. 2, 3, this is 1, right? This is the property, this is the algebra of angular momentum, if you want, right? You're going to show that Poisson bracket satisfies the same and it is angular momentum is related to rotations. This is what this means, so we'll show this, but let's proceed slowly, okay? I have 20 minutes. Okay, so this is Poisson bracket. So this is equal to lots of vectors at this point. And this is delta 1 theta dotted with L. And remember, delta 1 theta is a constant, right? We don't have any position or time dependence in this. And this derivative stops acting here. And then dotted with, this dot is, already this has been taken care of. So this dot works with this R, right? Hopefully, it's not too confusing. Delta 2 theta dotted with L. That's how you do Poisson brackets and then swap it. Minus of d by dt. Delta 1 theta. Okay, right, that's just a definition here. This comes out in a sense, right? This comes out, but now let me do this separately here. So what is d by, or a gradient, d by dr of delta 1 theta dotted with L is equal to, let me write this as a gradient. Or let me write delta 1 theta on the other side, so this is R cross P, which is L, dotted with delta 1 theta. Right? The dot product, it doesn't matter how you keep it, so I kept the delta 1 on the other side so that gradient can see R. What is gradient of R? 1, very good. So this is equal to 1 crossed with T dotted with delta 1 theta. Cross and dot product can be replaced. So this is equal to 1 dotted with P crossed with delta 1 theta. 1 multiplied by the vector is the same, so it is P crossed with delta 1 theta. Manipulation using the ideas that we have developed earlier. But the simple idea is that this derivative is simply P. Whenever I take the derivative with R, I get a P. Okay. Do the same thing with P. Let's say L dotted with delta 1 theta. This is equal to minus of del d by dp. I'm putting a minus sign so that I can change the sign here, R P cross R dotted with delta 1 theta. Again, P satisfies derivative with respect to P times P is 1. That's minus 1. Cross with R dot with delta 1 theta. Replace dot and the cross, take out the 1. So it is minus R cross delta 1 theta. Agree? That's a manipulation, but now we can do that here, use that here. This is equal to position, then we take the derivative with position, so that's P crossed with delta 1 theta. And when we do the R, so I have to put in a negative sign here, so negative sign, and then the R crossed with delta 2 theta. And there is a dot product between these two. Cross product. Negative of P is R, so this is R crossed with delta 1 theta and dotted with this is P crossed with delta 2. Okay. Think of this to be in the front. I'm going to write that first. A cross B times dotted with C cross D as this identity that if you're used to index notation, remember the property of two Levi-Civita symbols, it's usually equal to first A dotted with C times B dotted with D. And then swap it. Minus of A dotted with D and B dotted with C. That's the property of a cross product. Use that in here. Or maybe do it here. So this is minus of P dotted with R delta 1 theta dotted with delta 2 theta. And swap it and change the sign plus P dotted with delta 2 theta and R dotted with delta 1 theta plus R dotted with P delta 1 theta dotted with delta 2 theta and the outer, right? So it is R dotted with delta 2 theta and P dotted with delta 1. The cancellation here, this cancels out exactly this piece. And whatever is remaining is another cross product structure there, which I can write it as, so this is let's see. So I want to write it as a cross product and a dot product, right? So that is, so this is P and R. So this is P crossed with R. And dotted with Q crossed with 1. P crossed with R and 2 crossed with 1. I think that's correct. Swap both so I don't lose a sign. So this is equal to minus it. So this is R cross P dotted with delta 1 theta crossed with delta 2 theta. And that's the same as saying delta 1 theta crossed with delta 2 theta, which was a total rotation there, right? That's what's the use of this. This was to recognize that this is the total rotation dotted with L. That's what we learn out of this. What that means is that now going back. Summary is. Where's this part? Yeah. So summary is that. Poisson bracket of delta 1 theta with respect to L. Comma P is equal to delta 1 theta crossed with delta 2 theta divided with L again. If you were to do if you were doing quantum mechanics, you would say this is IH bar times delta 1 theta divided with L to 2 theta divided with L. Now it's commutator, that's equal. And just for your information, when you're doing in quantum mechanics, you don't depend on the product of it at all. It is independently done and it gives you the same result. You can sort of scrape out one of the delta thetas. And so that the interpretation here is that this is the algebra. So you can say this is the Lie algebra of angular momentum. So first interpretation of the Poisson bracket is that it is the Lie algebra. Lie algebra is whenever you have two operators sitting together. Another way to see it is that remove one of the delta thetas. Right? Just scrape it off, like take a dot product out. So I want to take out a delta 1 theta and I will take out a delta 1 theta here also. Write this as delta 1 theta. Right, swap the cross and cross and dot, and you have dotted with delta 2 theta crossed with L. And if I remove the delta 1 theta, what I interpret here is that L delta 2 theta dotted with L. We can Poisson bracket if we are doing classical mechanics. If we're doing quantum mechanics, that will be commutator. This is equal delta 2 theta crossed with L. This is a statement of how now I can generalize this any vector, like if, like, or you can say this is the transformation of L. If you're doing quantum mechanics, you will say the operator L of L under rotations. Remember, this is rotation, right? This is the generator of rotations. So this is how angular momentum, which is a vector in itself, rotates under rotations. Like even angular momentum is being a vector, it rotates. It doesn't have to be the angular momentum, any vector. If you have any vector, I didn't use A anywhere. Any vector A delta 2 theta dotted with under rotations. If A is equal to delta 2 theta crossed with A, if there is a vector, not every vector need to do this. If a vector transforms like this, then you say it is a rotational vector. Vector can be a Lorentz vector, rotation vector. Depends on the transformation. So under rotations, it has to transform. So this is the definition of vector. Let's say if here. The definition of vector. If it's a scalar, S. If you want to check that something is a scalar under rotations, it should give you 0. That's the definition of a scalar. Definition of vector under rotation. I say under rotation because there is a vector under Lorentz transformation. Also, this definition of scalar. And I can scrape out delta 2 theta also out of this. And then I get L. This time it's good to write Lj. Poisson bracket. Plus P is equal to, when I scrape out this delta 2, there is a cross that remains, that is the epsilon ijk. So this is in index notation, this is written as epsilon ijk. Okay. So Poisson bracket has more than one interpretation. The first one is, of course, it gives you the equations of motion or any operator, but it also, when interpreted correctly, tells you how transformations, how operators, or how just normal physical quantities transform. Like under rotation, I did this for rotation. You can do this for translation. Okay. First, you go back here, learn how translation works. What will happen if you're doing translation? I move this way, and then I move the other way. If I do it in the opposite order, what will happen? What will this be for translation? Is that clear what I'm asking? First translate, then do another translation, then change the order of translation. Do translation and then do the first translation again. What will be this that connecting the two?
The translation of path of one minus the translation of path.
Yeah, what is that? Physically imagine it and tell me.
The change.
Zero.
Very good, that's 0. In translations are commutative. Like if you imagine so basically there are two vectors, I'm adding two vectors, right? This is delta 1 epsilon, and this is, sorry, this is delta epsilon, right? Yeah, delta 1, and this could be delta 2. That's your two quantities. The additions, so vectors in what order you add doesn't matter. You will reach the same place. So these two will be the same place. So this will be 0, right? So what can you say about P then? What can you say? This is P. Commutation relation of P and P will be equal to, right? It will be 0 because this one is 0 now. This is a statement of translation. What will be the commutation relation of P, comma L? Right. I'm doing quantum mechanics now, like that's the same idea. How you will see this is, look at here, any vector transforms under rotation. Right? How does a vector transform under rotation? You see this, P is a vector, linear momentum, transforming under rotation. So what I'll do is I'll introduce a delta theta just for capturing that. So that's L. It's equal to delta 2 theta. So that's delta theta crossed with T. And that's the 1 over IH bar. Notice the interpretation I'm using. I'm not doing the algebra. You can do the algebra and you'll get the same thing. But I'm just asking, oh, how does that P is a vector, rotates under rotation, does this, and then you remove the delta theta because that was temporary, right? So this is P I, comma Lj, that's equal to epsilon ijk dk. We often do not see this written down there, but that is a corollary, immediately comes out. And the boost operator is a vector. What will be the boost operator under angular momentum? Same thing, P gets replaced with N. You can ask how P changes under rotation, how L changes under translation. You can ask how boost changes under translation, everything. So you can talk about all quantities. There are how many? 1, 2, 3, 4. 4 by 4, there are 16 major commutational, it's not 4 actually. There are 10, right? There are 10 operators here if you go by the components. So 10 by 10, there are 100 commutation relations here, but you can read it out. Like just by geometry, just by transformation properties, you can almost conclude about everything in there. Like there is some physical things some physical input that is needed for the boost, which I haven't talked about. There are some subtleties in there, but it has to be built and it comes out very nicely. I'll stop here though. We won't continue this too much. It gives you an idea and you should be able to build on it sometime wherever you don't need it. If necessary, this is there in Schwinger's quantum mechanics book. I'm doing it in the classical perspective, but the same idea. But it's done in quantum mechanics. Okay, thank you. Same algebra, Lie algebra. It's called the Lie algebra. Yeah. The same algebra. Good. And you show that